Let's look at this example solving a differential equation. It's a first order differential equation because I can see the y prime here, but it's nonlinear because there's a y underneath and a y. We can't algebraically manipulate this equation into like a y prime plus py equals q. It's not linear, is what I'm saying. So we need to try something else. It doesn't look immediately separable, but because I see this y over x here, it's making me think that maybe it's homogeneous. So in other words, it's making me think that I could rewrite it as y prime equals a function of y over x. If it was homogeneous, if it was y prime equals a function of y over x, then I would do the substitution, let y equal vx. V is a function of x is a function of x. I have to differentiate my substitution. So I'm going to do product rule. Derivative of the x, leave the v alone. Leave the x alone, the derivative of the v with respect to x. And I would substitute those two pieces in. So in place of the y prime, I would swap out the y prime with its derivative. What I'm really doing is I'm changing the dependent variable. I'm switching all the y's. Well, y is the dependent variable in the original equation. In my new differential equation, v will be the dependent variable. The independent variable will still be x. So I'm swapping out the y prime. Everywhere there's a y, I'm going to put a vx. So vx divided by x, that turns that into a v. Everywhere there's a y, I'm going to put a vx. Now, at this point, I see that my original supposition that this was a homogeneous differential equation is wrong. I can factor an x out of the bottom here. I can factor an x out of the bottom and cancel it with one of the x's on the top. But if this was truly a homogeneous differential equation, then when I did that substitution, it would end up being just a function of v, and then it would be separable. I still have some x's left over in there, so it's not homogeneous. But let's just take a look at what we did get. I can see from what we did get here that I can cancel a v off each side. Okay. Now, if it was homogeneous, it's not. If it was homogeneous, though, after I did that substitution, it would turn into a separable differential equation in terms of v and x. I would solve it, and then everywhere there was a v, I would put a y over x, substitute it back, and that would give me that implicit solution that I want. So we've established it's not homogeneous, but let's take a look at what I have here. I can now cancel an x off both sides. It's still not homogeneous, but it is separable. I can put all the v's on the v side, dv, equals cosine x dx. So it did separate. Let's integrate the v side with respect to v. So I've got v squared over 2 plus v. And we'll integrate the x side with respect to x. I need a constant on one of those sides. There is no initial condition given, so I can't figure out what the constant is. I'm not done yet, though, because I've gotten rid of the derivative. I've solved the new differential equation, but I have to put it back in terms of y's and x's. Now it's v's and x's. So everywhere there's a v, I need to put a y over x. So everywhere there's a v, I'm going to put back a y over x. And now my equation, my solution to this differential equation is back in the forms of y and x. There's my implicit solution to this differential equation. It wasn't homogeneous, but a substitution did the job anyway.